So this is a presentation of the project titled Missionaries and Cannibals by Team Fantastic Four. The group members are Harshni Babu, Sarah Elizabeth Paul, Sneha Biju Kurup, and Suzanne Sadiq. So first we'll go into the problem statement. The problem statement basically requires 3 missionaries and 3 cannibals to reach the opposite bank of a river. There is a boat that takes them across, but the boat can only consist of maximum of 2 and minimum of 1. We must ensure that the number of missionaries is greater than or equal to the number of cannibals on either side of the bank to ensure that cannibals do not eat the missionaries. So this is a problem statement, and we'll go into how we approach the statement. So this is a state space representation of the problem statement. It is represented as a 4-tuple consisting of NAS and GD as attributes. N is as follows. M consists of ML, which is the missionaries on the left bank. CL is the cannibals on the left bank. BL equals to the boat present on the left bank. MR is equal to the missionaries on the right bank. CR is equal to the cannibals on the right bank. And BR represents the boat on the right bank. BL plus MR is equal to 3 and CL plus CR is equal to 3, implying that the number of missionaries is the same and the number of cannibals is the same, which is 3. And then all of these should not be lesser than 0 and should not be greater than or equal to 3, because we cannot have a negative number of missionaries or cannibals or more than 3 number of missionaries and cannibals. And then BL and BR are binary representations for the boat state. And then the attribute A is essentially the state of the boat. So LR2C, LR1C, LR2M. All of this implies that LR means that the boat moves left to right. RL implies that the boat moves from right to the left. 2C implies 2 cannibals. 1C implies 1 cannibal. 2M equals to 2 missionaries. 1M equals to missionary. And so the start state is 331000, implying 331 is the number of is the state in the left side. There are 3 missionaries, 3 cannibals, and the boat is in the left side. And then the ending state ideally should be 000331, meaning everything has shifted from the left to the right. So the first algorithm that we use is the best first search algorithm. It is an informed search algorithm that expands the node with the lowest heuristic value. And the heuristic being used is that the missionaries left plus the cannibals left. It's a goal-directed search. It avoids exploring many relevant states, and it does not always guarantee the shortest path, and performance depends on the heuristic quality. Next, the next algorithm that we use is the breadth first search algorithm. It's an uninformed search algorithm that explores nodes level by level using the FIFO queue. No heuristic is used. It blindly explores all possible states, guarantees the shortest path in terms of number of steps, but not necessarily the fastest run time. And this is the analysis of the performance. So the time taken in microseconds for best first search is 834 microseconds, but for the breadth first search, it is lesser and 439 microseconds. The memory used in bytes is 1120 for the best first search, but for the breadth first search, it's 96. The number of states are 19 and 15 respectively for best first search and the breadth first search. So clearly breadth first search seems to be having an advantage. We'll be running the code later on to show it in real time. And then the results are that the BFS proves to be faster and lighter. There's less memory being used and there are fewer states. Best first search was more goal directed, but its heuristic leads to higher time and memory usage. In this case, the heuristic did not give a strong advantage. And the trade-off for BFS, implying breadth first search, ensures efficiency, while best first search depends heavily on heuristic quality. And now we'll just give a run through of how the code works. So ls, so we have our best first search and our breadth first search. We'll go through our best first search first. So I've compiled the code and then we'll run it, and this is how it looks when it has run. Wait, I'll just clear it up and show the actual path right now. Okay, So this is the path that we've explored, and these are all the states that have been gone through. The number of states are 19, and the approximate memory use is 1120 bytes. And now we'll go through breadth first search. Okay. The number of states that are being explored is clearly yes. There are only 15 states, and there's 96 bytes that are being used. And these are the states that it has gone through, and this is the path to the goal. So clearly, we see that in this program, in this specific problem statement, it is more easier. It is probably a better idea to use breadth first search. And these are the algorithms that we've gone through, and this was our approach. Thank you.